The particular solution for polynomial, we need to assume the particular solution to be also a nth order polynomial, which means that, for example, here we have g of t to be first order, and then we need to assume our particular solution to be also a first order polynomial. Okay, I suppose I need to switch here. So yeah, so I have a question is, if now g of t only has the first order term without the zero order term, do you think we need to assume xp to be a plus bt, or only xp of t equals bt? If you consider this is the A, this is B, who do you think A is correct? No one. Who do you think B is correct? Okay, no one. So, okay, so actually we need to assume xp to be a plus bt also, because even though we don't have 5 here, still we have a first order equation on the left side with the zero order term. So actually we still need the term a to eliminate this term. Yeah, so that's the case. And a special case for this special case for the polynomial is that if g of t is a constant, then we can assume that xp of t to be also a constant, because constant is actually a zero order polynomial. Okay. Yeah. So let's move on. So the next case is if g of t is an exponential function, e to the alpha t, So now we can assume xp of t to be a exponential function like this, So this is the second case. And also I mentioned the fourth case here. So this is the second case. This is the fourth case in that page. So if g of t is a polynomial multiplied by an exponential function, like this is an nth order polynomial multiplied by the exponential function, then we can assume xp to be another nth order polynomial multiplied by the exponential function. So let's see an example here. So I directly jump over this one, because the second case also include the first one. You can just let p of t to be 1, then that will be the case. And p of t equals 1 is actually a zero order polynomial, and it is just a constant here. So let's see an example. We have x double prime minus 2x prime minus 3x equals 6t times exponential to 2t. So the first step is to find the homogeneous solution. So it is the same as the previous page, so I don't repeat. So the next is to assume the particular solution, as this is a first order polynomial multiplied by an exponential function. We also need to have the polynomial of first order multiplied by the exponential function. This is exponential to 2t, so we have exponential to 2t here. And then this is a first order polynomial, so we have a plus bt, which is like a plus bt multiplied by exponential to 2t. This one is the particular solution, and then we now need to determine a and b. So now we plug in x of p to equation 2. So we have this term, and this term. double prime, and the original function equals this one. So it's just plug in equation 2. Now we can explain it. So we have double prime. So for this term, it is 4a times exponential to 2t. And then this term double prime will be a bit more complicated. So we have this term double prime will be 0. So just here, so and then we have this term, first derivative of this term, and then multiply by first derivative of this term, and then multiply by 2. So we have totally 4b exponential to 2t, which is this term. Also, we have the second derivative of this term, which is 4 exponential to 2t times bt. So we have this term. So this term is actually these 3 terms. So we have this term to be these 3 terms. And then subtract 2 times this term is, so first derivative of this term is 2 exponential to 2t, so we have a 2a exponential to 2t here. And then first derivative of this term is b times exponential to 2t, which is this one. And then the first derivative of this one is 2 exponential to 2t times bt, which is this one. So so for this one is actually this one. And then finally, this is the original one. We don't need to take derivative. So we just rewrite it here equals this one. So now we just collect the terms together. So we have t times exponential to 2t, t times exponential to 2t, also t times exponential to 2t, and then t. So we just collect these 3 times together. We have 4b minus 4b minus 3b. And then for the remaining terms are exponential 2t terms, so we just collect them 4a, 4b, and then minus 4b, not this one, minus 4a, minus 2b, and then minus 3b, minus 3a. So we all together with this coefficient for exponential 2t, which is equal to 6t times exponential to 2t. So we have 6t exponential to 2t plus a 0. I just write this term, which is actually 0, but actually you can see that this 6 should be equal to this term inside the brackets, and this 0 should be equal to these green terms inside the bracket. So we have actually 4b minus 4b minus 3b, which is minus 3b equals 6. And then also we have 4a cancel, so we have minus 3a plus 2b to be 0. And then with 2 unknown and 2 formulas, we can solve for a and b, which means that xp is actually minus 4 over 3 exponential to 2t minus 2t exponential to 2t, which is actually this 2 term, and the complete solution is the complementary solution plus the particular solution. Any questions? Okay, so the next case is the sinusoidal function. So sinusoidal function is I think it is the most useful case with the constant case. As long as there's constant or sinusoidal, it will be the most useful case. And maybe also this one, exponential times the sinusoidal. So actually this is sinusoidal, which is the third case in the previous slide. So for the third case, it is sinusoidal function, which includes sine or cosine, and then exponential times sinusoidal is the fifth case. This is the fifth case. This is the sixth case. So actually, for the sixth case, I don't think it will appear often. Yeah, I don't see it yet in bachelor study. But anyway, for the completeness of this set of theory, I just include it here. But actually, all these three can be regarded as the similar types. So for sinusoidal function, if g of t is sine beta t or cosine beta t, or include them both, then for the particular solution, you need to assume it to be a cosine beta t plus b sine beta t. And for the fifth case, if g of t is an exponential function times the sinusoidal function, then yeah, we can assume xp to be also an exponential function multiplied by a cosine beta t plus b sine beta t. And for the sixth case, if g of t is polynomial multiplied by exponential function multiplied by the sinusoidal function, like this, Pn1 times exponential alpha t times sine beta n or cosine beta t, then we need to assume xp to be another polynomial with n order, and then multiply by the exponential function times cosine beta t, and then also sine beta t, and then add them together. So we have a polynomial here and here. Yeah, so yeah. Okay, so here let's see an example. So this is only the third case. So if we have a constant coefficient linear ODE on the left side, and then we have g of t to be a sinusoidal function. So first is to solve for the homogeneous solution. So for this one, we have s squared minus s plus 1 equals 0. So it is actually a complex solution. So xc is exponential to t over 2 times c1 cosine square root of 3t over 2. So actually you can have, for this one, you can have s squared minus s plus 1 equals 0. So that you can have s equals to 1 over 2 plus or minus square root of 3i, something like this. So you can see that xc of t is, this is 1/2 here. The real part is 1/2. And then for the cosine and sine, we have square root of 3 over 2 to be the imaginary part. So we have here, we have it here. So this is the complementary solution. And the next is to determine the particular solution. It is actually a sinusoidal function. So we assume xp of t to be a cosine 3t, because this is 3t, so we also assume 3t here and sine of 3t here. Okay, so next we plug in this particular solution into equation 3, so that we have this term double prime minus this term prime plus this term equals 2 sine of 3t. So nothing but plug in this expression there. Okay, so next we need to calculate the derivative. So the second derivative of cosine is minus cosine, minus 9 cosine. So we have minus 9a cosine 3t. And then also we have the second derivative of this term is minus 9b sine 3t. Yeah, I'm not sure I miss. Yeah, maybe I missed one term here. Yeah, it should be like we should still have the first derivative. Oh, no. Oh, they are plus, so we don't have. So actually this is correct. And next we have this term prime. So we have minus 3a sine 3t. And then also we have 3b cosine of 3t. And then this is the original term And then next, we need to collect the cosine together. So we have minus 9a plus 3, plus minus 3b for the cosine, and then plus a. So we have these three terms to be the cosine, and then we also collect the term with sine of 3t. So we have minus 9b plus 3a, and then also plus b. So we have these three terms for the sine of 3t equals 0 times cosine 3t, because we don't have cosine 3t here, so we just make it like 0 cosine 3t plus 2 times sine of 3t. So in this case, the bracket in red color equals 0, and then the bracket with green color equals 2. So we have these two formula with two unknowns, so we can solve for a and b. And in that case, particular solution will be 6 over 73 cosine of 3t plus, minus 16 over 73 sine of 3t. Like this. This is the particular solution, and then plus the complementary solution to be the complete solution. So, any questions? Okay, so we can, so far there are fundamental rules for this set of rules, but there will be a glitch for this method. So let's see an example here. If we have a ODE like x double prime minus 5x prime plus 4x equals 8 exponential to t. So the first step is to solve for the homogeneous solution. So we let the right hand side to be 0, and then we can write it as a s squared minus 5s plus 4 to be 0. So we have the roots to be 1 and 4. So this is the complementary solution, c1 exponential to t plus c2 exponential to 4t. So now we observe that this term and this term is actually the same. If you just follow the previous procedure, you may assume that the particular solution to be a times exponential to t, if you just follow the previous procedure. And then you try to substitute this into the original equation, then you will find that left hand side will be 0 equals to 8 times exponential to t. Then you cannot find the solution for a, which means that the particular solution is not a times exponential to t. And it is very clear that because you try to solve for some exponential to st which satisfy the left hand side to be 0, and we already have this term to be the solution, to be the homogeneous solution, which means that if you just plug in this one into there, then it will be clearly 0 on the left hand side, which will never be equal to the right hand side. And alternatively, we can assume that xp to be a times exponential to t and multiply by an additional t, like this. It is similar to this case. For this case, we have repeated roots, so we can have a c1 plus c2 times exponential to x1t. So for the second independent solution, we need to multiply by t. And now if it is just... And now this term, the g of t, has the same term as the homogeneous solution. Now we also need to multiply the original xp by t, then this one will be the solution. This one will be the solution. And then if you just plug in this term into the equation 4, then you can find a to be 8 over 3, minus 8 over 3. So finally, you can find the complete solution to be this one, c1 exponential to t plus c2 exponential to 4t minus 8 over 3 t. So we have this term t here. So another, so another example is like if you have an equation like x, if you have an equation like x double prime plus 2x prime plus x equals exponential to minus t. So in order to solve this one, you can first solve for the homogeneous solution like this. So it will be s squared plus 2s plus 1 equals 0. So you can find that s to be minus 1 minus 1, which means that the complementary solution will be a plus bt times exponential to minus t. So actually this one is the same as g of t. So now we, of course, if we assume xp of t to be c times exponential to minus t, of course it won't be correct even if you just plug in c times t times exponential to minus t. It still won't be correct because it's actually this term. So in that case, the particular solution is excited to the square term. So if we have a zero order term, then you multiply by t. If you also have the first order term, then you multiply it by an additional t until there are no the same term. There is not the same term in the complementary solution. Then it will be good. You can just check it by yourself. You can try to plug in this one into the original equation. Then you'll be able to find c. And the complete solution to this ODE will be a plus bt exponential to minus t plus ct squared exponential to minus t. Of course, you need to find c need to be determined by plugging this one into the original equation. So this is a small glitch. It may exist for others case. For example, if we have something like x double prime plus 2x prime plus 2x equals exponential to minus t cosine t, like this. So if you try to solve this one, you have s squared plus 2s plus 2 equals 0. So s will be minus 1 plus or minus I. So usually in electrical engineering or ECE department, we usually use j rather than I. Usually j is actually the same as I, which is the square root of minus 1. But as you know, in electrical engineering, we usually use I to stand for the current. So we generally use j to represent the imaginary number instead. So sometimes I may try to write j, then you should know. So actually for this case, s squared plus 2s plus 2 have this root to be minus 1 plus or minus I. In that case, the complementary solution will be exponential to minus t cosine t plus sine of sorry, we need to have the constant before that. C1 cosine t plus C2 sine of t. So actually this term is actually the same as this one. In that case, we need to assume xp to be t times exponential to t's a cosine t plus b sine t, like this, which means that we need to have a t here. Yeah, so as much as we have the same term g of t to be the same term as we have in the homogeneous solution, then we need to multiply by t until there are not this term in the homogeneous solution. Yeah, you may ask why, but you can just follow the previous case. You can just assume, suppose, yeah, because very trivially we have a g of t to be here, so probably you can assume that xp of t to be h of t times exponential to minus t. Then finally you can find that and then you just plug in this one into the original equation. Then finally you can find that h of t to be a second order term, like that. Or similarly for this one, you can just but the calculation might be complicated, but if you are curious, then you may try to plug in xp to be exponential to minus t, a cosine t plus b sine t, something like this. Then you may be able to solve for that equation. Okay, so that's the glitch for the method, and we just try to fix it. So next, we talk about the initial value problem. So usually for an ODE, not only we would have not only the ODE itself, but also some of the initial value. Some of the initial value. It is like, yeah, so as long as we have a equation like x double prime plus x equals 4t plus 10 sine of t. So it consists of a second order ODE, and then on the right side, this is a first order polynomial. This is a sinusoidal function. Also, we have initial value. For first order and zero order and first order. So still first step is to let the right hand side to be 0. Let the right hand side to be 0. And then we have x double prime plus x to be 0. So we have s squared plus 1 to be 0, s to be plus or minus I. So we have a xc of t to be c1 cosine of t plus c2 sine of t. So this is the first step, the complementary solution. And then the next step is to assume the particular solution. Actually, you can do it one by one. You can have a xp1, you can also have xp1 of t to be a plus bt, and then plug in the original equation without this term, and then you may be able to find a and b. And then the next step is to have xp2 of t equals ct cosine t plus dt sine of t, and then plug in the original equation without the 4t, and then you still find. But actually, you can just make xp of t to be this one plus this one, and then all together you plug into the original equation 5, and then you can be able to find a, b, c, d all together. So we have double prime here. So double prime for a plus bt will be nothing but 0. So we don't have the first term here. So for the second derivative of this term will be quite horrible because t times cosine t and then double prime will have 3 terms. For second derivative of dt cosine of t, we'll have another 3 terms. So yeah. But yeah, of course, some of the terms will be vanished because the second derivative of t will be 0. So we only have 4 terms here. And then we have the first derivative of this one. No first derivative. We only have the original equation here. So this term is easy. And then finally, we try to collect the terms. So finally, we have a plus bt here, which is 4t, which is 4t. So we have a to be 0, b to be 4. And then we collect the cosine of t. We also cosine the cosine of t. Because as we just plug in t times cosine t, t times sine of t here, you can find that minus ct cosine t, ct cosine t will be cancelled. And then dt minus dt sine of t, and then dt sine of t will also be cancelled. So we only have sine of t, cosine of t here. And finally, we can find that a to be 0, b to be 4, c to be minus 5, d to be 0. So the complete solution will be c1 cosine t plus c1 sine of t plus 4t minus 5t cosine t, like this. So we only have 4 terms here, and then if we don't have the initial value, then is already done. However, we have initial value here, so we need to do the 3 prime, which is to determine the C1 and C2. So to determine C1 and C2 will be easier, which is to say, first we need to determine x prime of t by taking derivative of the complete solution, because we need to evaluate the first derivative as 0. So we need to find the expression first. So we take the first derivative of xt, which is minus c1 sine of t, because cosine, the derivative of cosine is minus sine. And then the derivative of sine is cosine, and then 4t, the derivative is 4. And then the first derivative of this one is minus 5 cosine t plus 5t sine of t. Okay, so now we have xt and x prime of t. So now we can find x evaluate at 0 by just plugging in t to be by substitute t to be 0. So we have a c cosine 0, c2 sine of 0, 4 times 0 minus 5 times 0 equals 5. So finally we can find that c1 to be 5. And then we can also evaluate x prime of t as 0. So also we plug in t to be 0, so we finally find that c2 to be 2. So finally, we find that the solution to this equation with this initial value to be x of t to be 5 cosine t plus 2 sine of t plus 4t minus 5t cosine t. Okay, any questions? So actually later we will use